In this video, I would like us to look at equations for planes. Now, these objects, these geometric objects, planes, will be sitting in 3D space, and so we have to collect the various ways in which we can specify a plane. So let me just give you, just quickly try to sketch a plane. Of course, there is already one here. It's the plane of this whiteboard, but I will try to do a decent job at giving you a nice representation of a plane. So we would like to express all points in that plane using an equation. So what kind of data do we need? Well, let's say that here is the origin, O. What sort of data would enable us to express all points in the plane using an equation? Well, for example, if we would have a point in that plane that we would know, let's call this one P, and two vectors in that plane. So both of these vectors sit in that plane. Let's call these V and W. So if these vectors sit in the plane, we can express all points in the plane. So for example, a point Q here, an arbitrary point, we could express it by saying, okay, let's consider the parallelogram that would be needed to have Q as the opposite vertex. So then what we have here is multiples of both V and W. So this is some scalar times V. So let's say this is S times V, and that vector is some scalar times W. So let's say it's T times W. Now if I add these two vectors, I go from P to Q. So all I need to do now is just go from the origin to P and then add these two vectors in order for me to go from the origin to Q. So if I want to express this vector, so first way of specifying a plane is to fix a point in the plane. Let's call this plane capital S. So fix a point in the plane and V and W along the plane. Then for an arbitrary point Q in the plane, we have OQ, this vector, this position vector pointing from O to Q, the origin to this point in the plane, will be obtained by taking the vector going from O, the origin, to P, this known point, then adding some multiple of the vector V and some other parameter times the vector W. This way we have two parameters S and T. They are real numbers, and together they will give us this equation for the plane. Okay, so let me turn that into coordinates. So in coordinates, if P has the coordinates P1, P2, P3, V has the coordinates V1, V2, V3, and W has the coordinates W1, W2, and W3, then this arbitrary point in the plane with coordinates X, Y, and Z can be written as P1 plus S times V1 plus T times W1. The next coordinate is P2 plus S times V2 plus t times w2, and the last one is p3 plus s times v3 plus t times w3. So this is the coordinate equation for a plane, for points in the plane. Okay. Now this is of course not the only way of expressing a plane or specifying a plane. We could also specify a plane with 3 points on it. So if we have a plane, let me draw another plane here, and we have 3 points that we know are on the plane, so that are not on the same line. So P1, P2 and P3 are points on the plane, are points on the plane, as then our arbitrary point Q, its position vector, can be easily expressed, again, going from the origin to, let's say, P1, and then use these vectors as our V and W. Okay, so the vector P1 to P2 and the vector P1 to P3 could be the corresponding vectors to V and W, and I could express a vector pointing from P1 to Q as such a combination of our V and W. So this is OP1 plus S times P1 to P2. That plays the role of our V up there, plus T times P1 to P3. Again, these two numbers are parameters. As they change, the point on the plane wanders around, but stays within the plane, stays on that plane. Okay, and well, of course, we could also have a third way of expressing a plane, and this third way is perhaps the most the least intuitive, but I hope this will make sense. To take a plane in space, pick a point on it. Okay, so let's say that we know this point P, and take a vector that is perpendicular to the plane. Now, of course, a plane in space has infinitely many lines going through it perpendicularly. There is only one line that passes through the plane at this point, such that it is also perpendicular to the plane. So let me try to draw this line. Now it goes below the plane, and here it comes out. Okay, so this is how I would like you to think of it. It enters the plane, passes through it at right angles. At right angles to the plane. So what I need now is a vector along this line. So let's say this is a vector along this line, n, which we call n because we usually refer to this vector as a normal to our plane S. Now if we have a point on the plane and a normal vector to that plane, we can express points on the plane as follows. So if I have an arbitrary point on this plane, Q, what will be special about Q, the reason it's on the plane, so fix point P and a normal N perpendicular to our plane. What's special about this point Q is that if I connect it to P, I get a vector that is perpendicular to our normal vector n. And that is, of course, true for all points in the plane, and is not true for any other points. So only points in the plane will have the property. Only points in the plane will have the property that that the vector PQ scalar multiplied, taken the scalar product of PQ with n, gives us 0, because they are perpendicular. Okay, so now of course we have to think of P as a known point, so its coordinates are known. Also the vector n, we assume that we know its coordinates, and it is the coordinates of the point Q that we are interested in. So PQ can be expressed, so this is PQ, it can be expressed as OQ minus OP. Okay, so if I use this relation and try and rearrange this equation, what I'll get is OQ scalar multiplied by n is equal to OP scalar multiplied by n. So using coordinates, if P has the coordinates P1, P2, and P3, and the normal n has the coordinates n1, n2, and n3, then an arbitrary point with coordinates x, y, and z will give us the right-hand side to be n1 times x plus n2 times y plus n3 times z. Remember, this is the formula for the scalar product of two vectors given by their coordinates. The product of the first coordinates plus the product of the second coordinates plus the product of the third coordinates equals the product of the first coordinates of n and OP, then the second coordinates, then the third coordinates multiplied. Okay, so this is our equation for the plane that is given by one of its points and a vector that is perpendicular to the plane. Okay, so before we finish, I would like you to consider the following problem, the following example. I will give you 3 points on the plane, 3 points on the plane, and so these are P1, P2, and P3. They have the coordinates 2, 0, 0 for P1. For P2, it's 2, 2, 1. And for P3, it's 1, 1, and 2. Now, what I would like you to do is to use these points and their coordinates to cook up a normal vector for that plane. So put these two figures together and try to use vector operations so that we'll get a normal to our plane, which has these 3 points. Okay, pause the video, think about this, and enter the coordinates of a vector that is perpendicular to the plane specified by these 3 points. Okay, I hope you have paused it and realized that in order to get a normal vector for a plane from 3 points on the plane, we have to take these vectors P1 to P2 and P1 to P3 and calculate their cross product, their vector product. So this is obtained by taking P1 to P2, the one vector, and taking its vector product with P1 to P3. If we do that, and let me just give you the answer, you will get 3, -1, 3, -1, and 2 for the normal vector. Okay, I hope you enjoyed this video, and I'll see you in the next one.